Morning, everybody. This morning, we have Stefano Francaviglia, who will talk about branch projective structures on surfaces.
Thank you very much. Thank you very much for being here. And thank you, the organizer, for taking care of our trips and everything. It was very nice to be here. So the title of the two talks is a branched projective structure. Where projective means complex projective structure, and I will talk about structure on oriented surfaces. So sigma will denote an oriented surface during all the talks. So the plan of the talks is the following. First, I will introduce a general setting of XG structure. Second, I will talk about branched structures. And third, I will speak about a couple of problems in the theory of branched projective structure, which are the realizability problem, and let's say the topology, the study of the topology of certain moduli space of such structure. And while discussing this problem, I will show some interesting source of projective structure. And I will discuss some recent result and some open problem in this setting. Okay. Today, I hope I will be able to discuss point 1, 2, and a little bit of point 3. That's the plan. Okay. So, what is an XG structure? X is a model space and G is a group of transformation of X let me write out automorphism of X. That's very loose at the moment, but it will become more precise in an example. So an XG structure on sigma is an atlas whose local charts are modeled on X and whose change of charts belongs to G. So is an atlas of pairs U alpha, phi alpha, where U alpha is open and the union of U alpha cover sigma is an open cover, and phi alpha is an homeomorphism from U alpha to an open set of X. Okay. What are the changes of charge? So you have you have U alpha, you have U beta, and here you are the intersection. So you have the finite map. Let me draw that picture here. You have charge phi alpha and phi beta. On the image of the intersection, you can use phi alpha minus 1 to come back to the intersection, then phi beta. So you can see this as a map from this open set of X to this open set of X. You call this map phi beta alpha. And you require that phi beta alpha is the restriction of an element of G. The first remark is that these maps are called changes of charge. These maps are local charge. The first observation is that the changes of charge satisfy a cocycle condition. Beta alpha is beta. And this is defined on triple intersection. Okay. So you have this kind of cocycle condition. So the first example of XG structure that you have in mind, you won't know perfectly. Example. So the classic example is Rn dpho Rn. If you use this definition with model space Rn and G, the group of diffeomorphism of Rn, you just get the definition of differentiable manifold. And then you have other metric example, for instance, like you can take S2 isom plus S2. So this is a spherical surface. I know that there are not many spherical surfaces, but we become more general during the talk when the branched will be inserted in the talk. So then you have the Euclidean manifolds. I always consider oriented stuff. So if I forgot to consider orientation specific stuff, in this talk everything will be oriented. Euclidean. And why not? hyperbolic surfaces. So these are the classical example of XG space. So there is a difference between this case and these three cases. The difference in these, the main difference between this Rn, for Rn and the other case is the nature of the group G. In this example, G is rigid. What do I mean by say that G is rigid? I say that means that this extension is unique. So if you have to map two elements of G such that F equals G on an open set, then F equals G, like analytic functions, right? So, of course, if your Rn is not rigid, yeah, right? And because you have partition of unity, it's not an analytic word, while isometries of these spaces are rigid, right? And an isometry is just determinant of the behavior on an open set. Okay, now we explode. We use the fact that when G is rigid, this change of charge is the restriction of a unique element of G, and these allow to define the pair developing map and holonomy. From now, I suppose G is rigid. So when G is rigid, if you have an XG structure, you can define a pair DH. This is called a developing map. This is called holonomy. The developing map is a map. The nature of this map is a map from the universal cover of sigma to the model space. Okay. And the holonomy is a map, is a representation from pi 1 of sigma to G. The definition of this pair is given by matching up the local charts. So here you have the universal covering, of sigma. Here you have your open covering U alpha, and you can lift. So okay, so this gives an open covering of the universal cover. Now choose a starting point called U0. I call U0 this set at that level. And then you have a well-defined map. If phi0, which is just the lift of the local chart. Okay. So this is well defined. Then you take an intersecting open set U1, right? And here you have the image of U1 is an open set V1. In the intersection, you have the change of chart. The change of chart, you can use this thing. V1. Yes, this is field 01, which is defined as above. And this is a restriction of a global element, of a unique global element of G. So I can patch the image phi01, the image of V1 by using the change of chart. This is, I just put this here. Then I do the same for the following set, U2. Now the intersection, I have the change of chart. So I can patch, I can glue V2 to V1 by using this change of chart. And then this pair I glue here. So this is an image of V2. This is P01 composed Phi12 of V2. And I can go on and define the developing map restricted on UI as the chart composed by all these change of charts. So P1, P12 of the local chart. These a priori depends on the path I chosen for going from U0 to U2 and so on. But by the cocycle condition, the cocycle condition assures me that if I start here and let's say U0, U1, U2, or if I say U0, U1, U2, I get exactly the same result because of the cocycle condition. So this is in fact well defined, and the cocycle condition give me a discrete version of homotopy of path, and so using the cocycle condition, I can show, since this is simply connected, that the developing map of this set is well defined, independently on the path of open set I chosen for reaching U2. Okay, so this is a well-defined developing map. And D, as promised, go from the universal cover of sigma to X. What is the holonomy? Well, the holonomy is basically this transformation. You can think this composition of change of the chart as a map from path to G. And by definition is a morphism, that send concatenation of path to composition, right? The cochain condition tells you that it is well defined up to multiple path. And then if you are in a situation in which you start from an open set U, choose a sequence of paths, and you arrive to another set here, which is the lift of the same open set. Remember, you started from an open cover here, you lift here, then here you have an open set U, and you have many covers here, right? Many lifts. So if here you have U prime, if they are the same, if they are the lift of the same object, they differ by an element of the group of deck transformation of the covering, which I denote by P1 of sigma. So this is gamma of U, and you can just define this element, this group element, H of gamma, as the composition of all the changes of charge that you use it for going from U to U prime. And this is independent of the chosen path. This is a morphism because it respects concatenation. It's a morphism from the deck transformation group of the covering to G, right? A couple of words. So first, this is called a developing map, and this is called holonomy of the structure. By definition, what you get is that D of gamma of U, but you can take gamma of X, is equal to H of gamma D of X. This is just by definition, because D of gamma U equal H of gamma D of U. This property is called equivariance. So D is H equivalent. As you can see, the holonomy depends on the choice of a starting point, right? For defining the path, and this is a usual phenomenon when we talk about fundamental groups. So there is a conjugation ambiguity, and the conjugation ambiguity also comes in another role. Now suppose that you have a sigma XG structure with DH, developing map and holonomy. Now you define another structure, sigma prime, by composing each local chart by an element of G. So sigma alpha. You choose G, a group element, and then you define sigma prime, same cover, G phi alpha. You take all this picture and you translate by using G. Okay? So you define you use the same base point to avoid ambiguity of the choice of base point. And what you get the D prime is just GD, just because you take all the local charts that you compose by G. And what happens to the holonomy? If here you have U0, right? Then you have the developing map. Here you have G, and you're translating everything. Now, here is D prime of U0, and this is D of U0. And this is D prime of gamma U0. Well, what you see is a conjugation. What is this image? You have to come back with G minus 1, go to H of gamma DD0, and come back with G. So what does it mean? It means that the prime of gamma U is G H of gamma G minus 1 T. So if you change the developing map by a conjugation, by post-composing by a group element G, then the holonomy representation changed by conjugation by G. Two such structures are considered equivalent. Okay. If you think to metric definition, they are isometric to structure that they're defined by a translation. So, are equivalent. And so, these also justify even more that the holonomy is not just a representation, it's a conjugacy class of representation. So, if you have a XG structure up to isomorphism, you have a well-defined developing map, which is well-defined up to post-composing by a group element, G, and you have a well-defined conjugacy class of representation G, representation H. This is called the holonomy. And the main property is that the developing map is equivalent with respect to the holonomy. Okay. So we still are in the unbranched world. A complex projective structure is a CP1 PSL2C structure. So a complex projective structure is just an XG structure where local charts take values in the projective CP1, and the change of chart are Möbius transformation. Okay? This is a uniformizing setting for studying the space X isom X, where X equal S2, E2, and H2. Euclidean, spherical, and the hyperbolic world are complex projective worlds. This is CP1, and rotations are Möbius transformation. These you can see as you can look at the plane as a C, which is in C union infinite, CP1, right? And the isometry group of E2 is a parabolic element that fixes infinite in the group of Möbius transformation. And this is just H2 is contained in CP1. You can see in many ways. I see H2 in CP1 as a upper hemisphere. So this is CP1. This equator is RP1. So in CP1 you have two copies of H2, let's say the positive one, and here you have a negative copy of CP1. Okay? And the isometry of H2 G is PSL2. Okay. so which is a subgroup of the Maven transformation. So all these cases are particular cases of branched projective structure. Now I want to focus on the role of holonomy. Right? So first, a remark or an example. The Teichmüller space is the space of, can be viewed as a space of hyperbolic surfaces. And hyperbolic surfaces are completely determined by the holonomy. Are isometric if they have the same holonomy. So these are very rigid statement. If you are in the world of hyperbolic surfaces, the holonomy tells you everything about the structure. This statement is no longer true when you go to the general setting of complex projective structure. This is no longer true. For CP1 structure. And I want to show you exactly what happened in the case of the holonomy of hyperbolic surface. So this is the grafting construction. So now I build for you two complex projective structure which have the same holonomy but are not equivalent. Okay? So I will start from sigma 0, a hyperbolic structure on sigma. So I have a very nice hyperbolic surface. Right? And this surface, I can picture like this, and I can consider the universal covering, which I uniformize as H2. Now I choose a simple loop here, and I consider the geodesic representative. The geodesic representative, here I have the lift of gamma, the universal covering, gamma tilde, and here I have all the other lifts of gamma. I have many, infinitely many lifts of gamma. So all of these are all lifts of gamma tilde, right? Now I make a surgery operation. I cut along gamma tilde, and then I see H2 in the projective sphere in that position. So this is H2. So now I have gamma tilde. Right. Now I cut here, and I insert a disk minus 2 points in the boundary. What is a disk minus 2 points in the boundary? I can draw that disk in this way. This is a disk without 2 boundary points. Why I draw this way? Because once I cut, in this picture, I just create some space because I cut it, right? And then I insert this disk here. From the point of view of the topology, I did exactly nothing because this is a disk. I opened the disk, I inserted the disk, nothing changed. Now I want to define a new developing map that will give me a new structure. So the developing map outside that disk is the old one. Now I want to define on the inserted disk and how I define the map on the inserted disk. These are 2 copies of gamma tilde. So the ancient developing map sent these 2 copies of gamma tilde here in gamma tilde. Now look at CP1 minus these 2 points, right? And open along gamma tilde, right? If you take a sphere and you open, then you open completely the sphere, and this is just a disk minus 2 points. You insert that disk in that space. Another way to say this is to say that I cut the universal cover along gamma, and then I glue a cut CP1 along gamma tilde, and then I pass together these 2 spaces. So another way to say this is that here I have gamma tilde, here I have gamma tilde. So when I define the developing map, this is the old developing map. When I arrive to this boundary, I just switch to CP1. I insert all the CP1. When I arrive to this side, I exit that way. Okay. If you think this is the same of saying that I'm here, I enter in CP1, and then I exit. So on this disk, I just make a complete tour of CP1. So the result is what I call grafting of this curve. Of course, you have to do the same operation simultaneously on all the lift of gamma. So for extend. Okay. This is the developing map. Now you have to take the action of the group, right? When you do this, and you consider the action of gamma on gamma tilde, gamma on gamma tilde acts by translation. So you let gamma act by translation on this disk. And the action is just, you let gamma act on this picture by translation. So here you have the whole CP1, right? So a disk minus 2-point you can see as a cylinder, an infinite cylinder because this 2-point does not exist, and here gamma acts as a translation, so the quotient is an annulus. And what you see at level of surfaces, at the level of the surface when you do this, is just an operation of cutting along gamma and inserting an annulus. So these new annulus that you inserted, they correspond to the quotient of this disk, which is nothing. This disk has the structure of CP1, is called grafting annulus. Okay. So this is often called a complete grafting or a 2-pi grafting because you inserted a complete copy of CP1, right? Yeah, you make a complete turn. You can make a turn of alpha if you want. You will define an alpha grafting, but in that case, you cannot complete in the same way the developing map and the holonomy of the structure change. So in general, you can do alpha grafting. The game works the same, but the holonomy of the structure will change. If you do the 2-pi grafting, the holonomy of the structure does not change. Why? Because outside the disk inserted, the developing map is exactly the same as before. So if you take a point X here and a point here, it of X, right? They have exactly the same image as before. So the equivariance that you had before is still the equivariance that you have now. So the equivariance does not, you can check at any point of your structure, the equivariance does not depend on the chosen point. So the grafting structure has exactly the same holonomy of the previous one. So these are two structures with the same holonomy. The holonomy of hyperbolic structure is the representation is Fuchsian, discrete, and faithful, and takes value in PSR to R. Why they are different? A priori, they could be equivalent. They are different because the holonomy, the developing map of the hyperbolic structure takes value only in H2. It's not onto, it's not surjective. While the developing map that I just defined and used is surjective because I inserted a copy of the whole CP1. Okay, these I miss a point, but since I do equivariantly, when I move in the other point, any point of CP1 is in the image of the structure, right? So the fact that the image of the developing map is or not the whole CP1 does not depend of post-composition. So any structure equivalent to the hyperbolic one cannot have a surjective developing map. So these structures are in fact equivalent. Okay, this is no longer true. So this example is not just an example in the case of the holonomy of hyperbolic structure. This is the general case. That is to say, this is everything can happen if you are considering CP1 structure with the holonomy of a hyperbolic structure. Here's a theorem. The original version of the theorem is celebrated theorem of Goldman. And then for the generalized in a general setting by Baba. The theorem is that if suppose you have sigma 0 hyperbolic structure on sigma, the holonomy H the Holonomy. Sigma CP1 structure with holonomy, with the same holonomy, let's say H0 with holonomy. Then they resist gamma such that sigma is the grafting along gamma of sigma 0. Now, gamma is not just a simple curve. You can make a grafting on a curve, then a grafting on another curve, and so on. Then there exists a multi-curve. You can make grafting on gamma, then another grafting on gamma, another grafting on gamma. So multi-curve is a bunch of curves, not intersecting curves, right, on the surface. And you can graph them using the same procedure simultaneously. So every CP1 structure with the holonomy H0 is, in fact, a grafting of sigma 0. And I want to give you at least the idea of the proof of this theory. So that's the statement, and that's the proof. So I start with the hyperbolic structure, right? Then I consider the developing map of the structure sigma. Right? So CP1, as I told you, is a positive copy of H2, a negative copy of H2, and they are divided by a copy of RP1. So this induce, you take the pre-image of such sets here, so you can split the universal covering of sigma in 3 parts. Let's say sigma tilde plus, union sigma tilde R, union sigma tilde minus. This is D minus 1 of H2 plus. This is D minus 1 of RP1. And this is D minus 1 of H2 minus. You have this splitting of the universal covering. Okay? You can play this game with any projective structure. The fact that the holonomy is a subgroup of PS L to R, because it's the holonomy of hyperbolic structure, tells you that this splitting is pi1 invariant. Because the PS L to R preserve the real projective space. So this induces a splitting of your surface. Sigma plus union a line, one-dimensional object, sigma minus. Right? So what looks like this splitting? You have your surface, and then you have so this curve that I draw are the real part, the real line, the pre-image of RP1, and the remaining part of the surface is divided in positive and negative part alternate. Any positive side is adjacent to a negative one near the real curve. So if this is positive, this is negative, this is positive, and this is negative. Okay. Okay, now I explore the topology of the I want to study the topology of the negative part. Okay. Here, I won't be specific, but it's important that everything is oriented. So, first of all, you can check that all these components inherit a complete hyperbolic structure, right? This is a complete hyperbolic structure, and this is a funnel which opens at infinity. So the hyperbolic structure of this is so metrically, this is a surface of this shape, right? And I continue on the negative part, like this, and so these lines are at infinity, right? Okay. So the hyperbolic shape of this surface is that way. Now you consider a component, a negative component. A negative component. So C is incompressible in sigma. A way how to prove this is that your surface is hyperbolic, so it's not a sphere. And if you take a boundary component, it has a geodesic representative either on that side or on that side. So since it has a geodesic representative, it is non-trivial. So you can consider a lift of C in sigma tilde. So now you have the universal covering, sigma tilde, and here I draw that way. That's C tilde. Now, this is just a topological object, right? But this picture gives you, suppose you have, this is C, a hyperbolic structure on C, whose holonomy is the restriction of the global holonomy to that fundamental group. So let me say with abuse of notation that holonomy of C is H0, is the restriction of the holonomy to this fundamental part, right? Now, this is a topological picture, and there you have the developing map. You can uniformize that picture using the hyperbolic structure used here, right? So you identify the fundamental group of C minus with its holonomy image. So now the holonomy is the identity in this picture, because you uniformize this universal covering such that the fundamental group here now is the image, is H0 of P1 of C. Just to have calculation simple. Now, the developing map of this structure go to H minus, H2 minus, because it's a negative component, right? Now you choose any rotation here and flip. Flip by a rotation. So now you have GD and GH G minus 1, right? So now GD is a developing map in H2. So the structure is unique. This provides a hyperbolic structure on the surface. The structure is unique. So this must be equivalent to my original structure. So this is conjugate to an isometry. So this is conjugate to H. So there exists maybe another element. So there exists G prime such that H equal G prime H G prime minus 1. But H is the identity. So by our smart choice here. So you have that for any gamma in P1 of C, H equal G prime gamma G prime gamma G prime minus 1. What does it mean? That every element of the fundamental group of C minus commute with G prime. So G has two fixed points. So the fixed set of G has to be invariant by any other group element. So this implies that P1 of C is elementary. So there are 2 points that are globally fixed. And a discrete subgroup of ESL2R, which is elementary, and loxodromic, is just cyclic. And so C is an annulus. So in this picture, that's good because negative part is an annulus and the negative part is an annulus. I could not have put this negative and this positive. Right? This is a posteriori. You start with the composition and you prove that the negative parts are annuli. These are the grafting annuli. These are just annuli, and these are the grafting annuli. So in this picture, you have a grafting here and another grafting here. So are the grafting annuli. Yeah, you're right. It's a grafting core. Yes, you're right. Thank you. The grafting is, so here you have the geodesic representative. Here you have the negative part, and here you have another positive part, and this you have the geodesic representative. So this is the grafting annulus. So the grafting annulus is topologically is a little bit larger. Thank you. Because everything is oriented. There's a subtlety when we say everything is oriented. Okay. If you don't take everything oriented, you will prove that either C minus the negative part are an annuli or the positive part are annuli. Okay, good. Okay, that's what I wanted to say about unbranched projective structure, right? And the flavor of problems that arise in general in the branched world. So let's now start to talk about branched structure. So first, as a warming up, I would like to show you some flat sphere and some spherical torus. As I told you at the beginning, there are not so many spherical surfaces, right? But you can have many if you allow some singularity. So here is a flat sphere. A flat sphere, I mean S2 with a Euclidean flat structure. That's a cube. A cube is flat, isn't it, right? That a cube is homomorphic to R2. Here, that you see, it seems that you see a singularity is not a singularity. This is a half plane in this direction. This is a half plane in this direction. This is a, so this is a flat structure on S2. You know that is impossible because here you see this line is not a singularity, right? You have half a plane here and half a plane here. But here you have a singularity because if you try to open up in a flat way, you will have something like this. Right? So that's a positive curvature concentrated on vertices. On the remaining part, that's completely a flat structure. You can play the same game and putting a spherical structure on T2. How do you do? You take a torus, right? A very symmetric torus. You take an axis and rotate by an angle of pi and take the quotient. By rotation. So here you have these two circles, right? So this part is identified to the back part when you rotate, and this arc is identified to this arc, is glued. This arc is glued to this arc, like a zip here, you close up. So the result is like this. These arc now are identified. Yeah, these two arcs identified. And here you have what remain of the torus, right? And this is closed, like an Nescafé sachet, right? And what is this? It's an Nescafé sachet. It's a sphere, right? So this is S2. It carries a spherical metric. Pullbacks to the torus. You obtain a metric on the torus with positive curvature, right? Strictly positive curvature at any point, and spherical metric on the torus. Now the torus it cannot carry a positive curvature metric, so the curvature must concentrate somewhere, and to compensate the positive curvature, there should be some negative curvature concentrated somewhere, right? Where is concentrated the negative curvature? The negative curvature is concentrated on those points. Because if you look at what is the structure around this point, if you look at the structure around this point, let's say you say the torus, so this now is the torus from the point of view of the axis. So this is the axis. And you don't see nothing more than this when you see it. This is the axis. And now you rotate that way. Okay? So this is the circle, right? No, this is not the circle, not that way. Yes, yes, this is the circle. So you rotate that way. So if you take a neighborhood of this point, right, its preimage is that or that. So if you look near this point, you have a map of the kind Z go to this square. The cover is a 2-to-1 cover of the disk, which is branched on the origin, right? So here, if you take an object here, it will have two preimages. So if you measure the angle with respect to the spherical metric in S2, since S2 is smooth, here you will measure 2 pi angle. Now you use the same metric to measure angle here, and now you will say that this 2 pi angle is a 2 pi, and here you have another 2 pi. So exactly as in the cube, here you have a missing angle. Missing angle is positive curvature. Here you have an extra angle. Extra angle is negative curvature. Here you have 4 pi angle, 4 pi angle, 4 pi angle, 4 pi angle, right? So here is where negative curvature is concentrated. And negative curvature appear as an extra angle. And you can check by using triangulation that with this phase of angle, you make computation and Gauss-Bonnet is satisfied. So there is no violation of Gauss-Bonnet. This is the average characteristic is 2 and the average characteristic is 0. So if you make the computation of curvature, taking into account the extra angles, everything will be fine. So this is the example that you have to take in mind when you talk about branched structure. So what is a branched structure? Is a XG structure on a surface structure on sigma where local charts are either homeomorphism or are allowed to be of the form z goes to z to the n. Right? You can play this game. We wrap around many times, and a local chart z go to z to the n. If you have here a structure with an angle 2 pi, you will have angle 2 pi times n. If there is some angle, some definition of angle. Okay. So you have the same definition as unbranched structure. Local charts are allowed to be branched covering. Now, the change of chart you define in this change of chart you define similar way. So if you have alpha, beta, you have so here you have phi beta, phi alpha minus 1. Okay, phi alpha minus 1 is not defined. if this is a branched covering, this is not one-to-one, it's not injected. But you require that this is well defined, and it is a restriction of G. That means that if here in the middle you have a branch point, the same behavior on both local charts. Yes? Well, this you can define branching structure when your local space is a surface. We are talking about structure on surfaces. If you have an XG structure where X as a model space is a two-dimensional manifold, you can define the same. Okay. So as you see, I didn't put the word definition because just what I want to say, the definition is the same. You have just to be careful to some detail, but it's the local charts are branch and covering. When you define change of charts, you cannot just say I consider f alpha minus 1. You just say that this is well defined and belong to G. Yeah, or the topological form of it is okay, conjugate this is conjugate to this card. There is an homeomorphism on an open set of the open disk. You don't need a complex structure. You say that topologically the local chart is topologically conjugate to this. Right. Well, this is I mean, at the end I will talk about CP1 structure, so everything will be will be complex. Okay, but it's not a matter of the complex structure, it's just topological definition. The local charts are of the form means topologically conjugate. Okay, you can define the developing map and the holonomy in the same way. So the developing map will be a map which has some branched points, right? Okay, and but the holonomy will be defined exactly at the same way. So when I will talk, the talk is on branched projective structures. So the notation is BPS is a branched projective structure, is a branched CP1 structure on sigma. Okay, 1 minute left. Okay, some example. You already imagine that branched covering will provide example. So, example. If you take any CP1 structure and take a branched cover of the structure, you will get a branched projective structure. Covering. BPS. Just the second example, then I will stop. How you build projective structure in a different ways, cut and paste. That's a procedure very similar to that of grafting. When we were defining grafting, we removed 2 points. They were the fixed point of the lift of gamma, and that point were on the limit set. Everything was fine. If you do the same construction in a generic way without removing points, you will introduce branched point. So you take here you have a BPS or branched or not. Here you have another BPS, right? Now, suppose you have a local chart here, and the local chart which are equivalent from the projective point of view. So you can pass from one to the other with a maybe transformation. This is always possible because the image is in CP1. Now, take a segment here and take a segment here. Cut these two segments and paste. That means that when you arrive here, you jump here. And then when you go around the surface, then you go here and you came outside here, right? This is the result, topologically. Just the connected sum. Okay. And if here you have a structure and here you have a structure, here you created, you have 2p angles, and here you have 2p angles. So you create 2 points of angle 4p. So you create 2 branched points, right? So this is a general construction of producing branched projective structure having in hands unbranched one. Okay, for today I stop here.